Okay, let's talk about another way to derive the hat matrix. And this might be a little bit appealing to some of you. So if you're interested in avoiding taking derivatives, especially derivatives with respect to vectors like we just walked through, this is the proof for you. So you can avoid taking the derivative with geometry. So recall that I mentioned that there was a geometric solution to this least squares problem that we're trying to solve. And so basically y minus y hat, or epsilon, this error term, is orthogonal to the column space of x. And that's the way that we can minimize those squared errors. Basically, using geometry, we know that we're going to end up with a minimum error here if we make sure that it is orthogonal to our column space of x. And so what I mean by orthogonal is perpendicular. So I talked about this a little bit in the last lesson, but basically imagine that you have this space spanned by x, and so the column space of x here is this hyperplane. And we've got this vector y here, and basically we're trying to find some space in this x column space that's going to minimize this error. And the way that we do that is basically by finding the line or the vector here that's perpendicular to this error term, or this y minus y hat. And so we actually can use some geometric facts to be able to determine what this beta hat is going to be given this rule, given that I want my y minus y hat to be perpendicular to this x space. So let's remember some geometry facts here. What does it mean to be orthogonal? So this might be a little bit of a review from some of your previous classes, but two vectors, u and v, are orthogonal if the dot product of u, v is equal to 0. And in vector form, we can also write this as u transpose v is equal to 0. So in our case, u here is going to be x, and v is going to be y minus y hat, which we could also write as y minus x beta hat. And so I've plugged in that fact here. I've said I've used that x transpose times that y minus y hat, so y minus x beta hat, and I've set that equal to 0 because that's going to ensure that these two pieces are orthogonal to each other. And so what I want you to do is now, using this, I want you to solve for beta just using basic algebra. So I'm going to give you a couple minutes to work through that. All right. So let's walk through how we would do this. And so if we were going to try to solve for this, the first thing we would do is pull this x transpose through. And so we'd end up with x transpose y minus x transpose x times beta hat. And now I'm going to move this x transpose x beta hat over to this side. So I have x transpose y, x transpose x beta hat. And so this should look really familiar. We're getting back to kind of where we started in the derivative form, except notice we didn't have to take a derivative. All we had to use was this fact about orthogonality that we know from geometry. And now I can get this x transpose x back over here on this side by taking the inverse, and so I'm left with just beta hat on this side. And so we've solved that beta hat is equal to x transpose x inverse, x transpose y. Woohoo! Okay, so now let's get the hat matrix. Why is it called the hat matrix again? Because it puts a hat on y. And so if you multiply y times this hat matrix H, you get y hat. So we're going to calculate H now using this beta hat that we just derived geometrically. And so remember that y hat is just equal to x times beta hat. And we know that beta hat is equal to x transpose x inverse x transpose y. And so if we multiply that by x, we end up with x times x transpose x inverse x transpose y. And so now we want just this h, we just want the hat, so let's cancel out our two y's, and we end up with the hat matrix is x times x transpose x inverse x transpose. So this is our final conclusion here. The hat matrix here is x times x transpose x inverse x transpose. And there you have it.